now. So good afternoon, everyone, and welcome to our new webinar on artificial intelligence for the energy transition. My name is Sylvain Lecorf, and I will be co-hosting this event with Anne-Laure Cellier for these 2 nice hours that we're gonna have. So this afternoon we will have a new format for the webinars. So we will be listening to 2 research presentations. Each of them will last 30 minutes. These research will illustrate these presentations will illustrate the research of HEC Paris on this theme, AI for energy transition. And then following these 2 presentation, we will start at around 3 p.m. Panel discussion. So our speakers will be joined by Victor Martin from TotalEnergies to discuss more broadly the challenges surrounding AI for energy transition. So we'll have 2-hour events until 4 o'clock. So just a few words before we start. You may ask your questions to our researchers and panelists all along the event on the Q&A section of your Zoom presentation. So you please use this Q&A section to ask your questions and not the chat. The chat can be used only for technical problems. So if you've got issues with sound or video, just use the chat for this. And then the researchers will reply directly to your questions in the Q&A section after their presentation. And if your questions are more broad or more general, then we will ask them with Anne-Laure during the panel discussion to all our speakers. And note that if a question is asked and is of some interest for you, you can also upvote this question in the chat so that Anne-Laure and myself will know that this is an important question that should be prioritized with respect to the other. And just one last word for our speakers. So you will have 30 minutes each, and 5 minutes before the end, Anne-Laure will just raise her hand to warn you that you are close to the end of your presentation. So now it's time to start. So we are really pleased to start this session with the first presentation by Damien Ernst, who is a professor at the Université de Liège, and is also now an invited professor at the TotalEnergies Paris. And he's going to talk about reinforcement learning for electrical markets. So Damien.
Thanks a lot. Thanks a lot. I hope you can hear me well. Thanks a lot for this presentation, Sylvain. So I'm going to talk about the energy transition, electricity markets, and the use of reinforcement learning for solving the many decision-making issues that you face when you work in these thematics. So very few people know it, but electricity markets are really complex structure. You should see them as a really complex environment that are organized more or less according to the figure that you see here on the left of the screen. So you have generation companies that sell electricity through what we call a wholesale market to retailer. So retailer, it's basically the company which is selling you your bill at the end of the month. It's EDF, it can be Alterna, it can be TotalEnergies. So we have many retailers in France, more than 20. They sell also electricity to the large consumer that interact directly to the generation company, and the retailer, they send you, they sell you electricity. Okay, so what you need to realize is that the electricity, it's a commodity which is sold quarter by quarter on the electricity market. So your retailer is buying your electricity, the amount of electricity you consume, every 15 minutes. So, and he needs to buy exactly the amount of electricity that his customers are going to consume during for every quarter of the year, every 15 minutes of the year. It's what we call a market period. And the games, really the games of this market are continuously evolving very rapidly, and you have new market models that are proposed, and it makes the interaction with those markets more and more complex. Let me explain you the main different types of markets that you have. Okay, so you need to realize that for every quarter, a retail will have, or a large consumer will have to buy the electricity that its customer or that is consuming itself. So the first type of market that you have is what we call the forward markets or the future market. There you can buy electricity years in advance. 6 years in advance, you can already buy. So here in 2022, I can buy electricity already for 2028. So you have what we call this forward market. And when you interact with the market, you need to know exactly when and the amount that you are going to buy in this forward market. Then you move closer and closer, you know, to the market period under concern, and then the day before, okay, you have what we call a day ahead market. You have around 30% of the electricity which is sold through this market in Europe. So this is what we call a centralized market. The different participants submit their bids to the market, and then you have a centralized clearing to maximize what we call the social welfare. It's a huge optimization problem which is solved. Then you can play with this market. And this market, so you buy the electricity for the next day, it closes at noon, okay? You know exactly once this market is clear, the amount of electricity you have sold or you bought through this market. And then at 4 p.m., before the next day, so 4 p.m. today, we'll open what we call the intraday market. Okay, so the intraday market, it's really what we call a bilateral market. So you have bid and offers for buying or selling electricity. You can interact directly with this market. And this market, you know, for buying electricity, let's say for tomorrow between 2 p.m. and 2:15, you can buy electricity, let's say till 1:45 p.m. So till up to 15 minutes, you know, before you know you enter into this market period. And well, this is to give you an example of the different products that you may have in the forward market. To give you an example of what the prices are, this is an example. For example, it was on last Friday. You can see that you can buy electricity on Apex Spot at a price, if you look below the screen, in 2025 at 74 euros per megawatt hour for all the quarters of the year. Okay? That's what we call a cal product, a calendar product. Okay, so for every quarter of the year, if you buy the same amount, it will cost you, for example, 74 euros per megawatt hour, a little bit more in 2024 and a little bit more also in 2023. Well, you know why? Because we are facing a huge gas crisis for now, which is why the prices are very high. Look, for example, if you want to buy electricity for every quarter of February this year, okay, so next month it will cost you 254 euros per megawatt hour, top line here of the array, okay, the table. That's an example of the forward product. So myself, what I'm doing, well, that's part of my research. I'm using reinforcement learning techniques, you know, to replace traders and to interact directly with those markets. Okay, so what is reinforcement learning? It's a subfield of artificial intelligence where you have one agent that interacts with an environment and he takes decision and he observes the effect of this decision on the state of the environment, you know, and he helps also, and that's a key feature of reinforcement learning, he gets at every time he takes an action, he gets what we call a reward, you know, and his goal is simply to maximize this reward. So I'm using these techniques, you know, for interacting with those markets with a lot of industrial applications. So now I have designed software that are really running for customers that really interact with those systems. So why reinforcement learning? The first reason, when you interact with market, you know exactly well, what is your reward signal? You know, when you use reinforcement learning, for example, in robotics, you need to define what is a reward signal, the numerical signal. When you interact with the market, it's very simple. It's the money that you are making. Okay, so you can clearly state, it's very, very easy to state a problem of interaction of reinforcement learning or interaction with electricity market by using reinforcement learning. Second, reinforcement learning are really techniques, that work very well when you take decision where you take sequential decision and when you have a coupling between the different decisions. So you need to take a smart sequence of decisions. It's not just one myopic decision. You need to take smart decision over the long term. And that's exactly what you need to do. The reinforcement learning techniques are specialized, really work well in such a setting. And when you interact with electricity market, you face such problem because you have a sequence of markets, and also you need to play a lot with the flexibility of the system, batteries, load flexibility, to translate, to shift load over time, and it creates coupling in decisions. So that's the second reason why reinforcement learning works very well. And finally, reinforcement learning are techniques that are able to work without any models, by just interacting with the system and in highly stochastic environment. And that's exactly what you have when you are dealing with market. You cannot modelize everything, and you are dealing with a lot of stochasticity, and even more stochasticity now related to renewables. Okay, so I won't enter into really the technical details of what we have done, but one of the most successful applications that we have for reinforcement learning for interacting with market is really the design of an agent which is able to interact with this intraday market. This is this new type of market that has appeared, and we have designed a software, able to interact with this market while at the same time, controlling a battery. So you have a battery, you are a trader, you have a big battery, okay? So with this battery, you can basically store energy, buy electricity at one market period, sell it at another market period, and make money. So here is really the structure that you have for the intraday market, and you need to realize the complexity of those markets, because at every instant, okay, you have access to a huge order book that you see here on the top right of the screen. In this order book, these are really bits where people detail what they are ready to sell for electricity or to buy as electricity, the amounts and the price. Okay, and you need to grab these bits in a very smart way. And every bit, for buying or selling electricity, okay, refers to one market period. Okay, and for the next day, you have 4 times 24 market periods. So it's 96 market periods, and you have thousands and thousands of bits that arrive, and you need to select them. And you have also a battery that you need to control, charge, discharge a battery at the right time so as to maximize your profit. So it's really a trading problem where you have also a battery. The generic reinforcement learning scheme is the following. You have a reinforcement learning. Well, if you look at any book in reinforcement learning, you will see a picture, you will see this scheme. You have a reinforcement learning agent. It takes an action on the environment. It gets a state and a reward. For the problem that we are tackling, what is the learning agent? It's really the entity that controls the battery and determines the interaction with the CID market. So really the bit that you are grabbing in the market. So this is really the agent. So he sends the actions, it's really the settings, the control settings for the battery, quarter by quarter, and really the bits that he grabs, okay? It applies this to the environment. What is the environment? It's the battery plus the energy market, and it gets in return the observation of the state. So the state is the state of charge of the battery. Okay, he knows exactly, and all the information that he has about the market. It can be the order book, it can be a weather forecast, load forecast, and so on. And of course, he gets as reward the money that he makes during the market period. I won't enter here into the technical details, but for making this work, and we have collaborated, for making this work, I mean, you need a little bit to simplify the problem. Okay, you need, because these are very complex problems, so you need to do a kind of feature extraction to reduce the size of the order book. You need also to reduce a little bit the size of the action space and make several assumptions. But then going, when the algorithm that we have used for this is a batch mode algorithm. So we have really worked with the order book, okay, it's a German order book, okay, to train the agent. So in simulation, we have used, let's say, a standard batch mode reinforcement learning algorithm with deep neural nets, recurrent neural nets as approximation architecture. And then we have tested this strategy. And this is typically the type of result. So we have worked really with NG on this problem. And you earn, let's say, the gains that we made, you know, with respect to what they were making with their best strategy is around 4% higher. So it's very significant. It's a significant amount of money that you can make by designing, by using these, let's say, intelligent agents. So it's really 4%, around 4% better than what they could do. And they were pretty smart. You know? I mean, when you interact, you know, with these groups, you know, working with electricity market or trading electricity, I mean, you are facing very high profiles in terms of engineering. Many of them are holding, you know, PhD and thinking about those problems for many, many years. So very, very successful. There is now a new markets model appearing. You know, at the beginning, I showed you the classical market model, what we call decentralized, this wholesale market model. And among the many markets models that are appearing, you know, there is one which is very interesting. It's called the renewable energy communities. Okay, what is renewable energy communities? It's a set of actors. Okay, it can be you, your neighbors, a small factory that can trade electricity locally. So you can exchange electricity locally. So for example, if you have PV panels on your house, okay, and you produce at one point too much electricity, rather than to sell back the electricity to your retailer, because that's what's happening now, you could sell this electricity to your neighbors. Okay, that's a new concept that has appeared, you know, in the European legislation, and now many countries, you know, are implementing those concepts into their own legislation. It's going completely to change the way you are going to trade electricity. You can really now trade electricity directly with your neighbor. And this is a little bit the structure that you have. So you have many consumers, you know, and through a concept that I'm not going to detail of repartition keys, okay, quite sophisticated, you can exchange electricity with your neighbor. And what we have been doing, two things. The first thing is use these reinforcement learning techniques for controlling these renewable energy communities. When do you need to sell electricity to your neighbor? If you have a battery, you know, should you store the electricity? Should you sell it? And we were seeking to optimize, you know, the global benefits of the community. Standard reinforcement learning technique, it works very well. But if I'm talking with you about this application, it's because behind this application, you know, you have another problem that we have more or less discovered. It's what we call the problem of sizing these renewable energy communities. Basically, these are very complex control problems, controlling them. And before controlling them, you need to make investment, usually in these communities. What are the PV panels that you are going to install? Are you going to install a battery, not a battery? If yes, what is going to be the size of the battery? You know, how much energy it can store? What should be the power of the battery? You need to optimize everything. And it's a very, very difficult problem. And you, in the energy sector, you are more and more facing these very, very difficult investment problems. And these investment problems, you could really see them as big optimization problem where you need at the same time to optimize the investment and the control policy of the community or other, you know, structure in your energy system. Why? Because it needs to be a joint optimization problem because an investment has only value if you make a good use of this investment, the optimal use of this investment. So if you control this investment in an optimal way. So these were a little bit two-stage optimization problems for which it's very, very difficult to find solutions. And we have developed also new reinforcement learning techniques for, if you want, optimizing at the same time the investment. So reinforcement learning, the investment, it's really modifying the environment and the control policy at the same time. You could say the problem is a classical mathematical programming problem, use these techniques, but it doesn't work well, for example, for synthesizing these renewable energy communities, because you have too many non-linearity, it's highly stochastic, it doesn't work well. And you have also, well, reinforcement learning techniques, you know, that have been developed, but only a few papers for tackling those problems. And what we have proposed, it's a new type of reinforcement learning techniques where you optimize at the same time the environment and the policy. Okay, those are kind of hybrid techniques because you use a little bit the knowledge of some equations of the environment together with the generation of trajectories, you know, to compute gradients over the space of of parameters parameterizing the control policy and the parameters parameterizing the environment. It's a little bit here, it's a little bit the generic scheme that has been developed. Pretty standard, the way it works, it's defined here by this algorithm here. You select, you know, parameters at random, you know. You first define also a first control agent, you know, at random, and then, as it is emphasized here, you compute, you draw trajectories from the trajectories and the derivative that you have of the equations of the system dynamic. You can compute the gradients, you know, and you can converge, you know, towards optimal parameters. And that's typically an example, a very, very simple example, where you have a diesel generator. On the right, a fully off-grid system, a battery, solar panels, and a load. And what you want to do, you know, it's what you want to determine, you know, what are the best investment in storage, in PV panels, in diesel generator. So it's typically the size of those devices, so as, you know, to be able to cover the load at the cheapest price. We have used our algorithms, it's the blue curve, the called depth. We have compared it against the state of the art as a function. So you have the score as a function of the number of iterations of the algorithm. Very good performances have been obtained. The great thing is that those problems, you know, that we have been facing, you know, in the energy sector, mostly the energy sector, you face them, you know, in many engineering fields, you know. And for example, you are also facing those problems when you want to design, for example, drones or robots, you know. So you have the design phase, but the robot needs to, well, it is designed, for example, for a specific task. So you need to do also the design, okay, or the combined design of the robot, you know, and the control policy, so that it can achieve, you know, this task at best as it can, you know. And this is typically, I mean, we have taken the example here of a drone, you know. They need to follow here the task, the green curve, and we have used exactly the same algorithm, those that we have designed, you know, for this energy system problem, for designing at the same time, for doing the joint optimization of the drone structure and the control policy, with also excellent results obtained. So that these are typically applications, very good applications of reinforcement learning, and it shows you the many things it can do. I'm also working a lot, you know, on the control of the electricity grid, really what we call the grid. So you need to realize, you know, that electricity grids are really complex objects. They are really covering entire continents. You have tens of thousands of state variables in this system, and you need to control them. Okay, before, I mean, they were still complex, but quite simple compared to what we are facing now. These were two-layer structure. They had a two-layer structure. You had the transmission network and you had distribution networks. Okay, transmission network is the network operated by RTE in France. Distribution network typically by Enedis in France also. Okay. Distribution networks were operated according to what we could call a fit and forget doctrine. What does it mean? It means that they were building cables, lines, transform, and they were forgetting everything. There was no need of advanced control strategy. Now it's changing because you are connecting, renewables, storage to those grids, and it creates difficult, complex problems. Okay, so you are basically moving from a two-layer structure where you only had advanced control strategy at the transmission level towards something which is now a three-layer structure. So you have the transmission network where you still need advanced control strategy, distribution network also because of renewables, because of battery, because of EVs. And there is a third layer coming atop the two layers, related to the fact that you have also a super grid, which is a DC grid, which is coming at the European level and even at the worldwide level. And reinforcement learning also offers huge opportunities, for solving these very, very, very complex problems. Either by implementing directly controllers, that learn by interaction with the system, or by interacting with a simulator. We have very good simulator of electrical power system and learning the control strategies by interacting with this system. Finally, and I will stop with this because I still see that I have 4 additional minutes. There are very, very few reinforcement learning researchers who really work on power systems, very few. The main reason is that they they cannot build by themselves simulators, and often, the existing simulators that you have in the industry, they are too complex for them. I mean, you need to be very knowledgeable about those power systems, for being able to use them. And that's the reason why we have designed a simulator for power system using the open source software library GIM, okay, in which we have introduced, a model, of distribution network, okay. And for those who are really interested by working on the energy transition, on electricity networks, they could use, this simulator. It comes with a very nice interface for designing their own agent. And I will show with this. I will end with this very short video. Okay, you see here it's a distribution network. Here you have wind farm, you have an industry, PV panels, and so on. And look very well, what will happen here. That's a typical problem that you are facing in distribution network now. You are going to connect a lot of EVs, to distribution network. So we need to charge them. But when you charge all of them at the same time, it usually creates a congestion on the line. So you will see a congestion appearing here on the line. And one strategy that you could develop is, for example, to charge a battery, a big battery, when you are not charging the EVs, your electrical vehicles, so that you have more capacity, for charging, the EVs when you really need to charge them. You are not constrained, by the capacity of the line. And what you will see here is the results of we have trained an agent on this network using reinforcement learning, and you will see, I mean, it's quite amazing. You will see that he will charge the battery, okay, a little bit during the night when he doesn't use, the chargers for the EVs, and when it uses these chargers, okay, when the power here will be very high, you will see that it will discharge the battery so as to avoid a congestion here on the line. That's a typical control problem now that you are facing in a distribution network. Let me start the video for ending this talk and observe very well what is going to happen. Okay, you see this charge, okay. Then he stopped using, we charge the battery again, okay. charge the battery again, and then discharge the battery when it's charging, the EVs. Okay, right in time. Thanks a lot for your attention.
Thanks a lot, Damien. Thanks a lot for this. I would like to, for this presentation, I would like to remind all of you that if you want to ask any question to Damien, you can do it right now in the Q&A section. So Damien, I don't know if you saw, but you had one question not in the Q&A, but in the chat. So whether you can choose to answer directly in
chat is a discussion.
In the chat.
Okay. I will answer.
Yes, in the discussion.
Okay. Yes, you are right.
You can answer directly there, or keep the questions for the panel discussion.
I will keep the question because it's a very good question about minimizing also the notion of risk. Excellent question. So I will answer this question later on during
the panel discussion. We're going to keep it for the panel discussion.
Thanks a lot, Julien, for.
Okay, good. So
should I stop sharing?
Thank you for your presentations. So now we're going to turn to. Yes, we're going to turn to the second presentation. So that Sam can share his screen. I don't know if he can try. Yes, it seems to work. So we are really pleased now to welcome our second speaker, who is Sam Aflaki. He's a professor and department chair at HEC Paris, and he's going to talk about promoting energy efficiency using performance-based contracts and analytics. Sam, the floor is yours.
All right. Good day, everyone. It's an honor to be here and discuss this extremely important topic of energy transition, which is basically has been for a long time the focus of my research. Just to be clear, I am an associate professor of operations management in HEC Paris, and I have a little bit of background in engineering, but most of my focus of the talk today is going to be from a business perspective, in the sense that what I am searching in the use of AI for any problems, including the energy analytics, is to see how AI can basically help business solutions and the mechanisms through which companies can optimize their operational decisions, not from particularly the focus that Damien was talking about, in the sense of grid management, for example, or finding particular solutions for bidding for electricity, which are extremely important topics. But I would like to take a moment and basically present a different perspective of the usage of AI and analytics in managerial problems. As a fitting example, today I would like to talk about my own research on transition to energy efficiency. Now, the audience, I'm not sure how much the audience are familiar with the notion of energy efficiency, but when we talk about energy transition, there is always a talk of investment in renewable energy sources, solar panels, wind turbines, etc., etc. In a lot of people's minds, energy transition means to invest in, the so-called renewables, the green sources of energy. However, there is a second face to this coin of energy transition, and that is if we could reduce our energy consumption for the same amount of service that we get for the power. And as it turns out, that is the cheapest, fastest, and smartest strategy available for saving money as well as resources, and also being more sustainable in terms of having lower amounts of emissions. And that is the key to understand this energy efficiency, meaning usage of less energy for the same service. And this could be applied in various contexts. You can think about in the households, We've seen a gigantic transition toward, more energy efficient lighting fixtures, for example, water heating, cooking, and these are the percentage of energy that goes, or electricity that goes into various functions within a house. And what we could do, and as you can see, a big part of it is with the space heating and also cooling. Yes.
Yes, we have a problem. We are only.
I'm sorry to interrupt you.
What's that?
Yeah, we can see only your first slide. So if you're changing the slides now, we cannot see them.
Let me stop. Okay. Let me stop share and share the screen again. Yes. So you're seeing my second screen now, right? And I'm
yes, and now we see a new slide. Yeah, it seems to work. Yeah.
Okay. Perfect. Thanks for letting me know. So, I was actually talking about how energy is used within the households for different functions, and we are now, we have a pretty good idea about how much of this energy is used within the different functions, and as you can see, majority of it is for HVAC systems, and therefore, a transition to more modern energy efficient systems, including, for example, heat pumps and etc., is going to save a lot of energy with the same level of comfort. So that's the key when we talk about energy efficiency. And in my own research, my biggest focus was in the fact that, well, it's a different thing to talk about customer behavior and how customer behavior change in terms of reducing the amount of comfort is going to lead to better energy efficiency. But here I'm not talking about that. Here it's about keeping the same level of comfort for the customers. This is an example of the heat pump that I myself have installed at home. And basically what it is that it takes the air energy and uses the physics principles of thermodynamics to take the energy from the air, even at temperatures that are very, very low, and basically pump it to the house. Now, these energy systems, depending on, and the data that I have here are more in the American market, but in France, depending on what kind of heat pump you want to install at home, it's going to take anywhere between 5,000–6,000 to even 15,000 euros, depending on the power. Now, the key here is that if you do install one of these systems, then your energy consumption for the year is going to be 30% lower. Now, that in itself should be a pretty good proposition to make customers actually invest in a system like that, right? Here is another example that I would like to talk about, and that is industrial furnaces. And in a lot of industries like the cement industry, the steel industry, pulp and paper, pharmaceutical industry, a big function of heating or creating water vapor is a big function within the factory when we're talking about steel industry, industrial furnaces. Now, if you can change your industrial furnace, you can save energy up to 90%. Now, if you think about the operational benefits that creates for companies, you would say, well, it should be an absolute no-brainer for the organization to do this. However, things are not that straightforward, because if you think about this kind of change in the operations, it is creating gigantic disruptions within the operations of a company. And also, we are talking about industries that are in their maturity and therefore have been running for a while. Right? And they have been testing some technologies for a long time, and therefore there is an issue of trust, and which I'm going to talk about it and refer to as the issue of technology uncertainty. So when I talk about technology uncertainty, you should you should remember that I'm not talking about the true uncertainty with respect to the outcome of investing in that technology. We know a heat pump is going to generate a certain amount of heat, and it's actually much more reliable than, you know, if 15 years old, you know, gas system or even system based on fuel. It's not about that. When I talk about technological uncertainty, it's about in the minds of the client, what are they thinking about the benefits of that? So there is a risk associated with the return of the benefits. And I have, you know, a couple of research papers about what are the barriers toward investing in energy efficiency. And for a long time, I have been seeking, you know, the answer to this holy grail of what's going on, you know, if these energy efficiency systems, EE systems, I'm going to call them, are so beneficial from an economic perspective, from a sustainability perspective, it must be very easy for all sorts of clients to transit toward that, right? Here is also another example. So I talked about, you know, the example of a household. I talked about the example of an industrial example. Here is a public example where municipalities, you know, striving to change the lighting fixtures within the streets or within, you know, public buildings, et cetera, around 5 to 60% of reduction in municipality electric bills. So why is it that we are not seeing? In France, we are in pretty good shape, mainly because of the huge push from the state to and the huge incentives that the state has put in place for subsidizing these solutions. But when we go out of France in you know, markets that are pushing this a little bit less, the energy efficiency measures have been, or you know, a big opportunity to invest in, both in the private sector sense and also from a sustainability sense. Okay, now I talked about, you know, my own research about what is it that is our major barriers toward energy efficiency. And, you know, there are many barriers. Just to cite a few, you know, one of the most important ones is that customers just don't have the time to think about this. I always say, you know, in my talks, that one of the most important organizational resources, or one of the most expensive organizational resources, is management attention. And if you're thinking about like pharmaceutical industry, in which 2% of the total cost is about energy, obviously it's going to be very difficult to convince the organization to go through this transition of investing in a technology which in their mind is uncertain. So customer risk aversion is one of the most important you know, one of the most important barriers against investing in energy efficiency. Now, how do you basically overcome that, right? So if you think about it, customers say, well, I'm going to have to put in place, you know, $5,000, $10,000 in advance. And then I am going to get 50 euros off my electricity bill, or 60 euros off my electricity bill for each month. Obviously, from a behavioral perspective, that is peanuts. And therefore, if you look at individual customers, there is a huge inertia towards going into investment in those kinds of solutions. And that's why, interestingly enough, a new business model has basically been born to address these kinds of issues. Okay, so here is what ESCOs are. These are energy services companies, and you know, we have here you know, a representative of TotalEnergies. It's interesting that TotalEnergies itself is one of the major, what we call ESCOs, or energy services companies in France. It's an energy company, and also an energy services company. Now, what do energy services companies do? They provide the information, they provide the know-how, in some cases, what we have, and in different areas of the world, the jobs that these energy services companies do differ. It can go from just feasibility studies and information sharing to execution to financing the project, right? And that is the kind of key that I would like to enter in this discussion today, and that is, how is it that you can finance these projects without and at the same time overcome the issues that energy services company the issues that customers have with transitioning and investing in these kinds of solutions. And the major solution that ESCOs have come up with, this is a business that has been growing exponentially throughout the world, in China, in United States, and that is mostly thanks to these mechanisms we call performance-based contracts. Now, what is a performance-based contract? It's it has a long tradition in operations management. Generally speaking, a performance-based contract is a contract in which the organization provides the funding, and then the project savings is going to basically pay back for the funding. Here in France, this is not the case. The ESCOs are not providing majority of the finances, although there are cases that this happens. The majority of finance is coming from banks and also from the states through tax credits that the French state is actually providing. But the ESCO business model essentially is very diverse, very resilient, and it basically in which the ESCO pays the upfront tax, and it's the ESCO that is liaising with the bank and the finance provider, and then the savings of the projects pay back for the project. Now, we are in an AI webinar here. And if you think about, I talked about energy efficiency, if you think about what would be the application of AI in energy efficiency, if you just went out and Googled it, it's very interesting that there are very limited amount of applications that you can find. And the applications you can find is, well, you can use the AI for architecture and building design, and obviously that would reduce the energy consumption of your buildings, and therefore that is energy efficiency. Or you can see that given all these smart metering systems that have been installed in a lot of buildings, you can basically use AI or artificial intelligence for smart and autonomous energy management, right? Even you can think about, in addition to, making a building more energy efficient, now customers are installing rooftop solar, and therefore you can use AI, as Damien said, in a larger grid perspective, in which the grid is going to decide when and how much of the electricity that is generated by the rooftop solar is going to be fed into the grid. In industrial furnaces, for example, AI has been used to monitor the performance of assets like buildings or industrial facilities, to see if the energy efficiency of these are going to change over time, right? So to do preventive maintenance and those kind of things. Most importantly, what I have seen is that a lot of people are talking about predictive analytics for energy retail. What does it mean? That means that I am going to use machine learning, deep learning, artificial neural networks to basically predict how much the consumption of a particular customer, given the inputs of their building, the types of walls, what is the energy rating of the building is, etc., etc. And I am going to predict what is going to be the amount of load. And we all can understand, anyone who in the business of electricity would know what immense value that would have for better load management of the companies, which means better energy efficiency in a sense, and better energy management. Recently, people are thinking about household classification and personalized marketing, right? So they're using predictive analytics and deep learning to basically use the characteristics of different customers, given their age, their income, their level of education, etc. I myself have a couple of publications in this area on how you can actually sell energy solutions to the companies, and what would be the likelihood that they are going to adopt these kinds of solutions. Now, these are the classic usage of artificial intelligence for energy efficiency. But I would like to talk about a new perspective. Artificial intelligence, for the public who are not familiar, with the jargon, is something that, people think about the movies and how robots work and smile and fall in love, especially, out of everything. But those of us who know artificial intelligence and machine learning, we understand that, well, these things have been around for a while. It's essentially, some fancy way of running regressions and basically forecast, right? Now, it's I say fancy, but also very powerful, because if you basically combine regression analysis with, artificial neural networks, which is something that you can use and create deep learning algorithms, then the accuracy of your forecast is going to increase. Now, that, I would like to argue, has a lot of potential in going in new directions, rather than just using AI as some sort of crystal ball that predicts the future with high accuracy. We can use these solutions to basically have better contracting mechanisms to enforce or to encourage customers, for example, to avoid the barrier of uncertainty and all sorts of different problems that can arise from a performance-based contract, right? So the performance-based contract, basically, let me elaborate on that notion in this context of performance-based contracts for energy efficiency, although that's a much larger proposition that I am having, and that is, we can use the power of these models and techniques to basically alleviate the incentive issues that arise from these kinds of contracts, right? So here are a bunch of different types of contracts that are used in the ESCO business. I call them. So this, one of the most prominent ones are the shared savings contract. And this is a contract, for example, that Honeywell and Johnson Space Center of NASA had, in the sense that the Honeywell renovated one of their biggest buildings and then continued to receive parts of the savings. Now, parts of the savings relative to what? And that is important, right? So when you implement energy efficiency project, then consumption by nature is going to be lowered, right? Now, how much of that is related to the energy savings? So that is where AI is going to come into the place. I'm going to talk about it in a moment. Here is another type of contract. This is guaranteed savings contract, in which case, the ESCO basically guarantees that a percentage reduction in the consumption, and says that I am going to pay, for example, all of your consumption beyond this level. This is an example that a prominent poultry facility had. And the guaranteed savings was that if we retrofit your facility, the chicken's facility, these facilities are very energy intensive, in fact, because the temperature needs to remain almost constant. Otherwise, and that's why all the antibiotics and et cetera, the flu is a bigger problem in chickens than in humans. So in this case, you've got a contract, and this is a different contract. Shared savings and guaranteed savings are different in their nature. Here's another one, the chauffage contract. The French should understand this contract very well, because the word is French, and it's used in all over the world. And the idea is that the entire energy consumption of a facility is outsourced, right? So in the sense, you are, as the ESCO invests in retrofitting the building, et cetera, and then instead of selling energy, they are going to sell the energy utility, in the sense that, we are going to sell this number of lumens of light or this amount of temperature, et cetera. I have a research that looks at these issues and contract design. And in all over the sectors, different sectors actually have different amount of untapped potential in industry, transport, power generation, and most importantly in buildings. And this is one of the things that we are seeing, that the energy efficiency is really staggering in the building sector. We can have a lot of improvements in that, right? So what I am interested in my research is how can we why is it that the customers are not investing, as I mentioned, but also how we can alleviate that using these different contracting mechanisms, and most importantly, in the research that I am in the process of starting with TotalEnergies, I would like to see how we can use the power of these artificial intelligence and machine learning techniques to design contracts that work. So here is, the way that I'm looking at the problem. ESCO offers a contract with a fixed fee and a variable fee, right? So usually this is a 2-tariff contract in terms of, the amount of investment. The client accepts or rejects it. If the client accepts, then the ESCO basically decides how much energy efficiency measures or investment they are going to have in the client. And then client, after that, is going to basically decide how much consumption they are going to have. Now you can see right away how much of a complex problem this is, right? Because the ESCO's payment is now going to depend on the client behavior. Once you change the walls or fixtures and windows, et cetera, then you're going to see that the clients are going to become more lax, and basically the base level for which you're measuring your savings is going to change, right? So I'm going to skip some of the detailed mathematical details of this problem, but the contract design is going to show that there is if you go through the analysis, you will see that there is this huge efficiency gap between what we call the first best model, where the ESCO is going to be able to observe the entirety of the customer behavior, right? And when in the case that it is not, right? So you see, there is going to be an efficiency gap. And the major insight that we have is that now you can alleviate that efficiency gap by using AI and analytics. Now, predicting customer demand is not only to basically optimize the load, right? But also is going to depend on, is going to allow us to do the contract design better, right? And basically overcome the issues that arise from changing customer behavior, what we call the rebound effect. The issues that arise from having the client being risk aversion, because what we can do is then, using predictive analytics, we can simulate and therefore guarantee the amount of money, or contract over the amount of money that customers are going to receive from the project. Now, there are a bunch of other questions that I'm interested in is, what is going to, how this differs in different sectors, right? So how should TotalEnergies contract for the different sectors of the customers, right? We have the residential customers, we have the government, public sector, we have the industries, and we have all sorts of different types of contracts: shared savings contracts, guaranteed savings contracts, and also chauffage contracts, and also a host of other types of contracts. In fact, I am looking at basically, let me skip all of these. I'm looking at designing a general type of contract, right, that is going to be allow us to address the issue of inefficiencies or client uninvestment in a serious manner. So to conclude, energy efficiency investment has a lot of room to grow, right? That is a big part of energy transition that is not discussed as much as, transition to renewable energy sources. Performance-based contracting and ESCO business model are crucial and key in this transition. And then the idea of contract design is a very new application of AI and machine learning that we can use moving forward to help transitioning toward a more sustainable, greener future. Well, thank you so very much for giving me this time. I look forward to our discussions. I think I'm right on time.
You did perfectly on time, which is why I didn't even have to bother you, Sam. Thank you very much. Thank you, Damien and Sam, for two clear and relatively big picture presentations relative to what we typically talk about in our webinars. Damien's presentation allowed us to visualize the entire value chain in the energy sector and speak of relatively upstream aspects of the challenges related to energy transition. By contrast, Sam's focus sheds light on relatively downstream aspects of the facilitation of energy transition. And so I hope that we get to have a wonderful exchange with Victor Martin in a few minutes. Before we turn to our panel discussion, I'd like to invite Damien, though, to address the questions that he received about his presentation. Damien, do you want to handle the questions that appeared?
Yes, so the first question that I received is RL decision making. Is RL decision making applicable for grid when the country is changing its energy mix, increasing renewable energy, wind and solar share from 5% to 30% in a short term? I mean, it's necessary. I would say it's necessary, almost necessary, to use advanced control techniques when the system is changing so rapidly, because when you connect PV panels or wind farm, for example, to distribution networks, you start creating, for example, congestions on this distribution network, voltage problems, and I mean, you can solve them, by controlling in the right way the active and the reactive power that these devices inject into distribution network, and also other devices connected to the grid, storage, EVs, and so on. And it creates very, very complex control problems with a high stochasticity that you can really solve using reinforcement learning techniques. And I'm also the CSO of a company called Chief Scientific Officer of a company called Ology. And we are really commercializing, these advanced control scheme for distribution network operators. And we use advanced reinforcement learning techniques, artificial intelligence techniques, more generally, for solving, the control problems, the problems that I have just mentioned. And it's essential. If you do not solve them, I mean, you would have, to carry out huge investments in new cable lines, transformer into a distribution network, and that would make, the energy transition, much too expensive.
All right, Damien, you might have seen Julien Gorintin's question in the chat. You mentioned the only target is maximize PNL. Isn't the risk of the risk minimization taken into account?
He's fully right. He's fully right. And that's a drawback of the techniques that we have developed. And if you want, to handle using reinforcement learning techniques, let's say criteria that are not based on an expected value of the return, but also take into account the the risk, you would have to move towards what we call distribution reinforcement learning. But for me, it's a field where you do not learn, the expected value. Most of the reinforcement learning techniques, they learn an expected value of an optimal policy. There you learn, a whole distribution. You try to build oracles, that can give you for any policy the whole distribution of the returns, and based on those types of oracles, when you add an additional optimization layer, you can extract, the policy that maximize conditional value at risk and other criteria like this. It's an excellent research direction, and we should certainly investigate it. But these distribution RL techniques, they are so time-consuming when you want to use them, run them on a computer, and you need to do a lot of tweaking in the approximation architecture. So, okay, there is still research work to do, and for sure, it's an excellent and promising research direction.
Good. Maybe one for HEC Paris researchers. Thank you for tackling this question.
That would be a great research question, and it's a problem which is not well studied at all.
Well, wonderful. Let's see later on maybe what Victor has to say about that. If you don't mind, Victor, before I introduce you, we have one question for Sam Aflaki. Sam, you can see it in the Q&A. I'll read it aloud for our auditors. To what extent AI and machine learning can be applied by those ESCO who serve with limited scope, i.e. they perform detailed energy audit of companies and identify no cost to capital intensive energy saving opportunities, and then leave the implementation of EE recommendations at client end?
Well, that's an excellent question. I think right now there are some very interesting applications of deep learning and machine learning in prediction of the load, and therefore the load reduction as a consequence of implementing an energy efficiency measure to the buildings. So as I mentioned, this is a problem of what we call double moral hazard. On the one hand, customers don't trust the ESCO's estimation of the amount of reduction in energy savings, and the ESCOs don't have much idea themselves. I mean, they have their own techniques, but then it's going to be a random variable. On the other hand, the ESCO implements the process, and the customer is going to change their behavior. The rebound effect is going to occur, and therefore the ESCO's payments are going to be affected. So to answer your question, one of the sides is going to be alleviated, right? So if ESCOs can find ways to much more accurately estimate the amount of reduction in the energy consumption of the client, then the one side of the moral hazard is going to be alleviated, and therefore the efficiency gap that I mentioned to you is going to be alleviated as well. So right now there are some very interesting applications of essentially predictive analytics using machine learning to basically say, if we implement this, and this measure, your savings is going to be 25.7%, and that is and if ESCOs can do that in a credible manner, then it's going to be very helpful in increasing their business with clients.
Excellent. Thank you, Sam. And thank you again, Damien and Sam, for illustrating perfectly the very different angles that HEC Paris on the one hand and EPP schools can bring to these topics of energy transition. I'd like to now turn to Victor Martin, whom we have the pleasure to welcome today. Victor, thank you so much for joining us. We are very excited to have you. You joined TotalEnergies nearly 20 years ago after a dissertation in geophysics. You filled different positions in geophysics and economics in France, Angola, and in the USA. More recently, you worked on artificial intelligence projects for geosciences together with Google in California. And since last September, you are responsible for the Paris-Saclay numeric team in the R&D cell of TotalEnergies. There, you focus in particular on electricity and sustainability related topics. To start with, Victor, could you maybe tell us how TotalEnergies generally deals with the energy transition? And then maybe, of course, what role AI plays in the company's approach?
Well, hello, everyone. Thank you very much, Anne-Laure, and thank you very much for inviting me to this panel. I think both Damien's and Sam's presentation were very interesting, and I really look forward discussing with them on those topics. So first of all, I'd like to start with saying that TotalEnergies, maybe in France, you don't need to introduce so much this company, but we're a global energy company. We're historically more an oil and gas producer, but for a few years now, we've embarked in a transition towards a renewable energy and with a goal, and we aim at being carbon neutral at the 2050 horizon, and which is quite huge actually for an energy company. And obviously we have several steps on our way, and we have the ambition of being in the top 5 renewable energy producers in the end of the decade, as well as reducing our own energy footprint, our own scope 1 and 2 energy emissions by 40%, and the global content of our energy products that we sell, that's scope 3 emissions by 20% by the end of the decade. So that's the first steps we want to implement towards the carbon neutrality in 2050. To do that, obviously we invest in renewable energies. Today, renewable energies amounts for about a quarter of our investments. And when you look at how we prepare the future, and especially how we invest in R&D, those new renewables and sustainability subjects now have more funding than the traditional historic subjects of TotalEnergies, which is quite significant. So what does AI, to come back to your initial question, and now what does AI have to do with all that? Well, obviously AI is present today in almost every part of our lives, in almost every businesses, and energy is obviously not an exception to that. We've heard great talks of Damien and Sam around how we can, about the different markets, about how we can optimize the trading of the electricity, how we can optimize reaching an equilibrium in the electricity generation versus distribution, how we can try and leverage contracts to have more customers or to gain customers towards the energy transition. And obviously that are all topics that are important for us, Total, because we're TotalEnergies is on the entire spectrum from the production to the distribution of energy. We have B2B and B2C clients. But we also focus a lot on the production and how we can lower the costs of the production of the renewable energy, how we can improve their reliability, and also on the usage side, how we can improve the usage by making it more efficient and less carbon neutral. As you know, the electricity grid has several production components. Even through a normal day, you will have a lot of solar energy around noon, and towards the beginning and the end of the day, you may have to kick in some additional capacities depending on the other renewables. That would be, for instance, gas power plants. And so depending on the time of the day where you have to consume electricity, the carbon content will not be the same. So you may also want to optimize the time of the day when you can, when you have the choice of using the electricity so that it has less carbon content and helps towards the goal of energy transition, which is have lesser and less carbon in the energy that you use. So I've talked a lot, I've talked about the use, but maybe just on the production side, very concretely, a few projects that we have using AI in order to improve both the design and the operation of our facilities. Obviously, we have some activities, a lot of activities around the forecast. Being able to forecast the resource is extremely important. And for some project, it can make, obviously, the entire value of the project being interesting or being even negative. If you take the sunroof panels, for instance, depending on the orientation of your roof, depending on whether you have trees around them that can cast a shadow on the roof, the production of solar panels on the roof can be very high or can dramatically decrease. And so we have used AI in the past in order to, as a prospective tool for roofs, for houses roof, for residential buildings roof, to determine their tilt, their orientation from satellite images and see whether it is interesting or not for potential customers to install solar panels on their home, thus reducing their usage of the grid electricity and improving the overall carbon efficiency of the entire system. So that's one of the things for design, also being able to predict for our wind turbines, for instance, for our wind farms, being able to predict also the wind on the long and also on the short term, in order to ensure that we have the profitability that we expect. On a more operational basis, we also have used AI and reinforcement learning in order to optimize what we call the yaw control for the wind farms. For example, a wind turbine, the propeller can tilt a little bit, either up and down or left or right, from the axis of the main wind. And playing with that enables also to reduce the drag effect in a wind farm, because in a wind farm, you have several wind turbines, one behind the others. Obviously, the first one normally doesn't have so much turbulence in the incoming wind, but it creates turbulence for the next wind turbines. And this turbulence can reduce the electricity consumption, the electricity generation of the next turbines by up to 10 or 15%. That's an estimation from the NREL, which is a prominent research group in the US on this subject. So by moving a little bit the axis of the wind turbine, we can learn to maximize the overall production of the farm. And this is something that we've addressed with reinforcement learning in the past. And even have the research team has even filed a patent on that. This enables also to, in the future, also to assess the design of the wind farm itself and saying where it will be the most efficient to put the individual turbines, so that given the historical prominent winds, it minimizes the turbulence from one windmill to another. We also have studied on the solar side for the operations. One of the big problems we have on solar panels is that obviously we are going to put them in places where there is not so much competition with other uses and especially agricultural uses, which means that you may end up putting them in more desertic areas, in more in areas where they are more remote and difficult to reach. And one of the effects of that is that when you have dust or sand coming on these panels, if you're in the desert, then the production of this panel is going to drop, and it's going to drop significantly. But it can come from this, I would say, this source. It can also be that you just have a cloudy day or a cloudy month, and your electricity production is also going to drop, and that you cannot control it. But one of the things that you can control is having a crew coming to your facilities and try to clean the panels. But if you do that very often, first of all, the panels might be degraded by the cleaning operations, but also it costs money. And the more remote the facilities are, the more money it's gonna cost to you. So you need to optimize the timing when you are going to clean those panels. And this is a problem because you have to decorrelate from other sources other than soiling in order to be sure that the panel is soiled and you have to clean it. Eventually, there are all the different preventive maintenance tools that you can use and see how a parameter deviates from the normal, and which could be the sign of an inverter starting to fail, or the sign of a failure in any component actually of the electrical design of the facility. And so preventive maintenance has long been used in all of the industries, and it's also starting to be implemented in the renewable energy business. A last thing I would like to say also towards the use of AI for the energy transition is that the way that TotalEnergies envisions the future of energy has obviously more renewable energies, renewable electricity in it, more electricity, but we don't think that we'll be able to completely get rid of the traditional fossil fuels, even at the 2050 horizon. There are some usages, airplanes, for instance, some petrochemicals that are difficult to do, or almost impossible to do, or extremely costly to do at the moment without the fossil fuels. So it means that either us or other people are going to continue to use fossil fuels, even if the amount of fossil fuels will be much lower as it is today, but that will still be fossil fuels. So how to achieve net zero with that is by capturing the carbon that is emitted in the atmosphere by the use of those products, and then either convert it to other molecules or re-inject it where it comes from in hydrocarbon fields. And we are also using machine learning for that. The carbon capture, some of the designs of the carbon capture facilities use materials, special materials that have the ability to capture the carbon of flue gas, which contains CO2, and then release it afterwards when you apply steam on that. One of those materials is called MOF, like metal organic frameworks, and it's a kind of cage which traps the CO2 and then releases it when you have steam coming through the material. The efficiency of this is still a very expensive process, more than $100 per ton of CO2, which makes it, for the moment, not economic. But if you manage to improve the efficiency of the capture process, by using better materials for the capture, then you may reduce the cost of the overall process and make it profitable to capture the carbon either from industrial facilities where it comes out of which it comes out very enriched, very much enriched, or even for some projects with direct air capture, just taking the air from the atmosphere, which is much less enriched in CO2 and which will be much more costly. So designing those materials today, there is an entire field of chemistry that uses AI in order to calculate the energy of those molecules instead as a kind of pre-sorting of different molecule candidates that you want to evaluate. Before that, there were tools to do that. You could use DFT to calculate those energies using first principles, but this is a very costly process, and the more atoms you add to your molecule, the cost of those processes is exponential to the number of components you add. So you need to, when you deal with very complex molecules such as MOFs and materials, or even catalysts for CO2 conversion reactions, then you need to have an efficient process when you improve the efficiency of those materials and catalysts. And this can be done using AI, using banks of material properties, of examples of DFTs that you've calculated, of the desired output, stability, activity of the molecules. You can achieve having a much fewer good candidates that you can test, and so improve decrease the cost of the development of the new materials and improve their properties in terms of CO2 capture. So that's basically all the different tracks that we're following, I would say, on top of what Damien and Sam have been talking about for the production. We also have obviously tried some reinforcement learning techniques for the grid simulation and the grid optimization, and we faced exactly the same troubles as Damien mentioned, which was having data to play with. Transitioning to new energy means that we are doing things that we did not do before. So we have little data, sometimes no data, and machine learning without data is something that's quite difficult. So most of the time, many times, we resort to simulations to simulate the data that we want the algorithm to start learning with. And that's also something we've done, like the simulator Damien was talking about, and released also an open source simulator, which we have developed with the University of Stanford. So that's all I wanted to say as an introduction. One thing I wanted to pick up on from Sam's presentation is really about the behavior. I think Sam's point is extremely important. It's also this entire transition will not work if the behaviors of the actors does not change. And when we have risk-averse actors, it can be very difficult to make this transition effective, especially if in front of them they have AI-based systems. But I'm hopeful that maybe one day, I mean, when you use Google Maps today, most of the people by experience are familiar with these tools and know that the time that they announce are quite reliable generally, so they use it. And I think it's really through the usage and being honest with the uncertainties also with the clients that we'll also manage to do this transition and have our customers be happy with it.
But to be clear, at TotalEnergies, you currently do not try to facilitate that actively vis-a-vis customers in B2B or B2C? Do you have any actions that's directly at the consumption level?
Well, we are not, well, we have a few, we have a branch which is called Greenflex that is doing some consulting work. And as Sam said, I mean, consulting work with customers to try and improve their energy efficiency. We also are in the R&D stage, trying to see what we could do as an energy company. So both from the contract point of view, from the hardware point of view, and the power purchasing point of view, because we also produce the electricity, to improve the overall efficiency with our clients. And we have many research actions on that, trying to and implying also the EV charging stations. And it's a little bit like the simulation that Damien was showing. We even have I would say a test going on at the École Polytechnique with one of the students' building, where we have installed solar panels on the roof. There are EV charging stations in the garage, and we have some smart meters also everywhere to monitor the consumption. And the end goal will be to design management systems to improve and optimize the energy consumptions of this building and its carbon efficiency. So that's still a research projects for us.
At HEC too, and maybe at EPP as well, there are a number of psychologists working on how to make people, one, more aware of their energy consumption and how to accelerate and create a movement, if you will, towards lesser consumption. So there are tools, and we need many field studies and much help from companies to allow us to let us do that in research on the ground to see whether these techniques work. Sylvain, did you have a question?
Yes. So first, thanks a lot, Victor, for this really rich overview of the projects at TotalEnergies. First, before any other questions, I just wanted to add that, as you mentioned quite extensively, use of reinforcement learning and in talking about the performance-based contract, Damien and Sam, if you have any reactions or whatever, feel free to dive in. No need for a question, and I can ask other questions, obviously, but as Victor said many things, maybe you have a few reactions first.
Well, perhaps just a question related to the talk, this very interesting talk of Victor. I get the feeling that Total, you are missing big things now in the portfolio of projects that you have developed. It's the direct capture of CO2 in the air, okay? Electrolysis of water using decarbonized energy, okay? And then you use the so-called Sabatier reaction or Fischer-Tropsch reaction, and you are basically synthesizing artificial, carbon neutral fossil fuels, I would say. And this opens new avenues. You could install remote renewable energy hubs, I don't know, in Greenland, in the desert, without having without having any grid connection that take years and years to develop, and synthesize these fuels there and import them to big load center. I have personally studied a lot, these remote renewable energy hubs, even designing totally new grammars, for optimizing them, sizing a problem, control and sizing with batteries, to synthesize hydrogen, you can store CH4, for example, if you synthesize CH4. And I'm surprised that you are not studying this more, at TotalEnergies. And that's one of my main research direction, my main research objective here at Telecom Paris is to develop really these hubs, all the numerical aspects of the hub, but to go even much further and try really to build them with big company. So I would be pleased to work with you on this very, very ambitious topic. It's going to cost a lot of money, in the billions of euros. So I just want to warn you, it's not a small research project if you want to build this. But I mean, for big companies like Total, I mean, that's what you are paying for an offshore oil platform. Right? It's 4 or 5 billions of euros. So this is an amount of money that the company has. And I think you need to be more ambitious on this topic, much more ambitious.
So if I may answer, yes, I didn't mention the, well, thanks for the question, Damien. And I didn't mention the research on hydrogen because it comes out obviously of the AI picture, at least for the moment for us. That's currently a quite hot topic for us as well. I mean, trying to have electrolyzers that can produce hydrogen at the lowest possible cost is something that we pursue, and we have some fields of research and collaborations ongoing on this subject. Regarding Fischer-Tropsch, so that's a subject. I remember when I was a student, that was already a big research subject. And you're right. I mean, that's not something that we've looked at a lot. My guess is, and I'm no specialist in that, but my guess is it's because it's probably not cost effective for the moment. But I mean, when you put a lot of money into something, sometimes you have good surprises. So why not? Maybe. And I'm open to discuss.
I'm going to send you a paper that I wrote on this subject.
All right.
Where you have all the grammar that has been developed, you know, for studying these are really even pricing, you know. The energy which is generated by this is extremely difficult because it's pretty complex. It's not just about installing PV panels and you know, trying to assess the cost of your PV energy. It's really trying to assess, for example, the cost of CH4 if you produce it in Greenland when it arrives, I don't know, in Dunkirk, for example, in the LNG terminals in Dunkirk. I'm going to send you the paper, and I would be very pleased to discuss with you about this, yes, and to convince you to invest tens of billions of euros, you know, in those hubs. Yes.
Yeah, I would like to also thank Victor for basically agreeing with my proposition that in order for energy transition to be successful, we need to also understand not only the behavior, but also the incentives of the different economic players. By that, I mean, why is it exactly they would like to, and why is it exactly they are not, you know, moving toward that? And the answer to that are twofold. Number one are behavioral and marketing measures, which themselves need artificial intelligence. There are a couple of papers out there that talk about you know, how you can use AI to basically cluster and do feature analysis for different customer types, and then send customized emails to them with respect to the ways that they can actually improve their energy consumption. Now that is, you know, something that you know, I myself and my marketing colleagues would be very interested to do. But the second part is obviously that and we always say it in supply chain management, it's not about the behavior, it's about the incentives and the contract. So how do you make contracts that would align the incentives of these players with your incentives of, you know, optimal consumption? And that is something that, you know, to my best of my knowledge, no one has looked at. And the reason for that is simple, is because the performance-based contracts have been basically applied to a lot of very low-hanging fruits with no risks, with, you know, the amount of this being done, for example, in the residential sector is very, very low. There are a bunch of examples where, you know, a company takes over 100,000 apartments in a complex in China and so on and so forth, but not many of these with individual customers, right? From, you know, an ESCO. I mean, I'm not talking about the state incentives. And I am saying that, you know, there is ample data to show that there is gigantic amount of potential in this sector. And what we can do is we can use AI to kind of remove those barriers of double moral hazard, which I mentioned. But you know, as I mentioned, I am so excited to potentially work with you guys and have the data and look into this problem of optimal contract design to make the customers, you know, short of, you know, putting a gun to their head, to make customers behave the way that you are that you would like them to do, right? So through contracts.
Yes, there are a few aspects of that actually, if you look historically in France, at least, there were already a few contracts like that. If you think about it, we had what was called heure pleine, heure creuse. I don't know how you can translate that in English, but basically, if you use electricity at the peak consumption times, it's more expensive. If you use it outside.
That's called peak load pricing.
Yeah, exactly. Sorry. So peak load pricing, and I mean, there are multiple ways of declining that and make it profitable, both for the customer and for the distributor. So, and that's exactly what you say. That could be that's something that is contract based, because there are times of the day when the electricity generation is cheaper and is less carbon intensive than other times, and there are some types of loads that you can postpone through the day. I mean, dishwashing, as long as your dishes are clean when you come back in the evening, it's fine. EV charging, if you need 5 hours in the to charge your car and you're 10 hours in the office, it leaves you some space to optimize that. So there are plenty of ways, but that's and this is where it gets interesting, because with AI, you try addressing you start addressing both from the physical side, the production components and the prediction of the production components that make this type of contracts viable, and also from the contractual side that makes them interesting both for the customer and the producer.
Thanks a lot, Victor, for these reactions. I see that Gail joined us. I also saw that, Gail, you had a question for our speakers, but it was just sent privately to me. So I will leave you ask it a bit later. But first, I will have also on my side one question for Damien. Maybe a silly question, but I missed some technical parts of your reinforcement learning approach. And I was wondering, all these reinforcement learning algorithms rely on many assumptions, which I'm not sure I understood them on your side. For instance, we assume sometimes that the processes are Markovian. We also assume independency between agents, like the impact of the action of one agent won't impact another one to ease the training and validation process. Are these assumptions used in your tool, and how does this impact these practical applications?
Actually, I mean, when I say they rely on assumption, I should have been more accurate, you know. I mean, to have, let's say, performance guarantees, you know, you need to rely on some assumption to have performance guarantee, but they can work well even if all these assumptions are violated. So it's a difference between having an algorithm, using an algorithm in a setting where that you can theoretically study, you know, and having good performances on another setting. So I believe that they were, well, they are pretty robust in terms of performances, even when you start violating those standard assumptions that you make for studying them. Yes. So
okay, so what you're saying is that they can scale to really complex problems with a lot of interactions and dependencies, even if you don't know how to study them.
Yes, exactly. It's exactly this.
Okay, thank you. Gael, do you want to ask your question, maybe?
Yes, sure. Thank you, Sylvain, for giving me the floor. Hello, Damien. In fact, I did not show my pictures, but I was listening to you very carefully. And I have one question. Yes, you talk a little bit about hybrid approaches, where you describe the use of models jointly with learning, a learning process. And my question is linked to that. Can you re-explain exactly how the model is used and what is the gain of using the model in the whole process? And as a side question, I would ask, can you give us some hints of how the model is included in the learning process?
I'm going to be very honest in my answer, Gael. First, we designed these algorithms, you know, the first time we designed these algorithms, it was to optimize MCTS algorithm. It was like finding, you know, the best algorithm. So like also two stages, you want to find the best algorithm that is going to give you the best solution. Then we realized that the best way, you know, to sell our algorithm was to basically sell them as an algorithm to optimize both an environment and the policy in reinforcement learning. So we had the algorithm was using derivative, and we didn't think at that time that it would have been possible, you know, to do everything without computing any derivative. Then we submitted the paper to the Journal of Artificial Intelligence Research, you know, and you had one reviewer who pointed, you know, to a work where they were solving a similar problem, you know, without computing any derivative. Okay, so I believe that this work where you do not need to compute any derivative, well, these algorithms, they are much easier to use because, well, you do not need, you know, to compute all these derivatives. We have seen that they were less sample efficient than the algorithm that we have been using. But I'm not going to tell you that the algorithm that we have done that are computing derivative are better, you know, than the algorithm that do not compute derivative. Okay, I think it was a very interesting work what we did. And also in terms of problem statement, the benchmark, it's a very small community, only a few people are working on those problems in RL. So even the benchmark, you know, they were not well stated and so on. So now the research direction that we are taking, you know, is to extend to develop other algorithms that do not rely at all on the computation of derivative. And the research direction is pretty clear, you know, the work, you know, that has been optimizing at the same time the environment and the policy without using derivatives is based on the very early work that you have in policy gradient techniques in reinforcement learning. But you have had many other algorithms that have been appearing in this field of policy gradient. So basically, we are almost taking one by one all these algorithms. We have all the sequence of paper and adapting them to a setting, you know, where we optimize at the same time the environment and the policy. That's the story. That's the story.
Okay, thank you very much. And if we have time, I will be glad to extend the discussion with you on that to better understand how you couple these environment models without computing.
I will send you directly the paper, Gael.
Very good. Very good. Thank you.
All right. So thank you, Gael. Thank you, everyone. I see we have one last more broader question about the disposal of solar panel batteries. And whether you are already thinking of all the solutions that we're discussing are entailing a disposal challenge. Is that something that you've started talking about at TotalEnergies? And in our research community, is it something that our fellow researchers are aware of people working on? Maybe to
so the disposal, the disposal of solar panels. So that's a good question, and that's a tough one, actually. To be honest, it's not really my field of expertise, so I don't want to say anything inaccurate about that. For the solar panels, I don't really know. I'm not sure this is something. These are things that are that can be recycled. Probably a few components of metal can be taken back, but I'm not really sure. For the batteries, it really depends on the technology of the batteries that you're using. Today, there are many different technologies of batteries. Some are very recyclable, some are not at all, and there is the entire range in the middle. So it really depends on the technology that you're assessing, and the technology is related to the use. If you have a little storage space, then you need to use technologies that have a very high energy storage density. If you have more space, you don't have that type of constraint, and you can use technologies that can be more easily recycled. So it really depends on the use that you foresee on the type of batteries that you're using.
Okay, and I have a somewhat related question in terms of how you reason about data centers. In a previous webinar, we talked about AI and sustainability. And one of our panelists raised the issue that data centers are big. They're getting bigger than ever. They're getting, in his own words, insanely big, and they're incredibly energy consuming. I realize that at Total, it's probably not your key issue because of the specific activity of the company, but is that something that you talk about as well in your approach to AI in the energy transition?
Yes, that's one of the questions. When I arrived, there was already in September there was already a work group working on that. Basically, the data center problem is twofold: is how efficient your data center is, and second, how efficient your algorithm is, or how much calculation do you need versus the accuracy that is requested in the end. Right. And can I use an algorithm that is 10 times less, that has a little less accuracy, but that costs 10 times less to train? Today, just to give a perspective, IT usages, digital usages, is 4% of the total greenhouse gases in the world. If it was a country, it would be the fifth emitting country. It's expected to grow up to 10% in the end of the decade. So that's a huge problem, and most of that is due to the data centers. If you take one of the big AI models that has been trained, GPT-3, so that's a natural language model, it took them 10,000 GPUs to train over 14 days. The electricity consumption corresponds to 200 tons of CO2, which is the equivalent of a flight from Paris to New York. So it's not something that you are going to be repeating over and over, and especially in research. One of the good things we have in France is that the data centers that are located in France, they use French electricity. French electricity has 36 grams per megawatt of per kilowatt of CO2 emissions. That's 10 times less than in the US. So just by locating your loads in countries and in places where the electricity has much less carbon can have a big impact. And we see that when we evaluated our cloud consumptions, which is mainly in the US, versus our own data center consumption, because we have a supercomputer in Pau, in France, the balance was completely different. So yes, we are starting to think about that. We are not yet at the stage where we provide guidance to our scientists, to our AI engineers, or data scientists regarding the accuracy versus cost of calculation. but that's definitely one topic that we would like to work on and have guidance.
Thank you very much. Sylvain, is there any other question coming from our auditors or?
I don't see other questions, maybe in the Q&R. No, there was a comment, but no other questions from the Q&A, neither on the chat. So I don't know if you have a final reaction on your side, Sam, Damien, on what Victor just said before we close the session in 5 minutes.
Just a small remark with respect to all these data centers. Usually, you know, when big companies, you know, they store data, they do not only store data in one data center. They store data in several data centers to have redundancy. And they can choose also at one point of the day with which data center to work. And these data centers, if you think well, they give you finally an opportunity to balance load and generation at a worldwide level. Okay, so you may have, for example, in the US, a lot of renewable energy today. So you should preferably work, you know, with the data center that you have there, and more with the data center that you have in Europe when you have more wind in Europe and when the gas is less expensive in Europe. And that's the same, for example, for well, all these processes related to Bitcoin mining. So there are opportunities there, new opportunities. These IT loads, you know, they offer new opportunities, you know, for designing new schemes for balancing load and generation at the worldwide level, and that's not enough used or deployed nowadays.
There's a new branch of geopolitics getting born, in other words, right? Sustainability is not uniform the world over. Sustainability opportunities, at least for companies.
Yes.
Very interesting.
Exactly.
Maybe in closing, unless there are a few other questions from Sam or Victor, maybe Gaël, now that we have you, you could use a few minutes to show off what the center has been up to in the last few months.
Yes, okay, thank you, Anne-Laure. As I mentioned, I was with you all the time. Yes, so I'm very happy to see this webinar series. Thank you very much for the two speakers, the three speakers. It was very interesting and very nice. So, well, in these 2 minutes or the 4 minutes I have, I just would like to highlight a few of the program of HEC Paris. And in fact, one of the emblematic program of HEC Paris is to enable us to hire top-level professors to scale up and to gain in visibility and impact in AI and data science, both at HEC Paris and HEC Paris. And we are very glad to have hired 10 new professors, which are now in place, including Damien, who is one of these renowned professors that has been recently hired at HEC Paris. And also, besides this program of a new professor, and we have a number of activities and scientific and education activities organized by HEC Paris and around HEC Paris. This series of webinars is one of them. But we have also a series of reading groups, which are maybe a little bit more technical. The next reading group will be on the topic of uncertainty, and I'm sure it will attract also a great interest. And they will be organized every Tuesday, every second Tuesday in the month. So the next one will be on Tuesday, 8th of February. We have also large events organized, such as a very large hackathon that will be launched in the coming weeks. It will be a 5 weeks long event, and with this will be with a summit, I would say, in the first weekend of March, where we have this final running and in this during the hackathon, and it's open to all HEC and IP Paris students and university master degrees. And we will have also a ground symposium in AI in the beginning of June with top level speakers. So it will be between the 8th and 10th of June. We expect a very nice event at the time. We have also the annual summer school organized by HEC Paris. This will be beginning of July. And also maybe just to announce something which is not yet launched, but that we are discussing and that will come soon. It's we will launch a series of meetup events and probably will be organized a couple times a year, maybe 3 times a year. There will be Thursday, end of the day. And the first one will probably be in April or May or so. And this is just a pre-announcement of this. So just check your emails, check the announcement. We will be very happy to have you and colleagues and your colleagues in all these events of HEC Paris. And that's it. Thank you very much.
Thank you, Gaël. And may I mention the other side event of HEC Paris with Rexel on the 11th of February?
Absolutely, yes. I'm really sorry to miss this event. Please announce.
No, it's a little off the chart compared to the many other events the center is doing. On February the 11th, we'll have the pleasure to welcome on campus at HEC Paris, Etienne Klein, to come talk about gender balance in scientific careers. And we have a number of men and women on stage with us from our corporate donors and from our community of alumni and current students. So I encourage you to look out for the email announcing that event. If you can make it, it's one of the rare face-to-face events we're gonna have for sure in the next few months. And then you can also attend remotely, obviously.
Yeah, 11th of February, beginning of the afternoon, right?
Yes, 1:30 to 3. It will be short, 90 minutes with Etienne Klein on the topic. Thank you very much, everyone, for your attention. Thank you to our researchers. Thank you, Victor, for joining us today and providing a very rich exchange. We look forward to the next one, probably in April for this format, and hopefully in person.
Thank you very much.
Thanks a lot, Anu. Thanks a lot, guys.
A lot to everyone. Good afternoon. Bye-bye.
Good afternoon.
Bye.